Welcome, Mindsetters, to this grade 12 maths session. I have Mr. E.T. here with me today. Mr. E.T., what's going to be happening today?
Linear programming is one tool we're going to acquire today.
All right.
Yes.
All right. So while Mr. E.T. makes his way across there, I'm going to tell these guys what they need to do. E.T., see you now. So guys, you know the drill. Make sure you keep chatting to me on the page. You know the link, www.facebook.com/learnextra. And I've got a calculator from Casio and a labeler to give away. So guys, post. So get those questions in if you're lost anywhere, if you need help. If you want to help someone else, do it. The more you help, the more you post, the higher your chances of you getting one of these calculators and this labeler. So guys, keep posting, keep chatting. It's for you. But for now, I just want to send a quick shout out to Liberty for sponsoring, and Mr. E.T., take it away.
Thank you, Tai. Greetings to our viewers at home. Linear programming. Yes, it's another tool that we are acquiring. We have acquired tools like calculus and all. With all of that, we were able to optimize. That means maximizing and minimizing. We've been able to do all of that. Today, here is another tool. It is a decision-making tool about our ever-limited resources. Our ever-limited resources, such as cost, it optimizes the linear objective functions, such as cost and profit functions, using the variables that are subject to constraints. Yes, you have heard us say linear programming there. Our constraints are, literally linear, okay? Our resources will be quantified in terms of counting or measuring, and typically we're talking about money, time, space, area, distance, and the numbers that you can accommodate in a certain space or something. And when we talk about money, we will be talking about income and cost or profit and loss. Those who are doing accounting, economics, they've already heard of that terminology. And yes, it's not only resources. We have linear constraints, like I've mentioned already. And these constraints are represented in the form of inequalities. Our inequalities will be in the, typically the equations like AX plus BX. Let's pick a pen there. The likes of AX plus BY less than C, or AX plus BY, that was supposed to be Y there, greater than C. All right? And there are, I think it's a warning here, there are several types of constraints that you have to underline there. Your constraints will either be very well expressed, like an equation like that. We call them explicit constraints, or they will be implicit, a bit unexpressed. Like, if I'm going to produce Kumbis and some sedans, there's no way I'm going to produce negative cars. So, typically if I say A is greater than B, automatically I'm saying to you B is less than A. So that's what I mean by implicit constraints. Then you have redundant constraints, those that are mentioned, but really they have no impact on the problem that you're doing. All right? I'm going to look at an example where we can take linear constraints, make sure we can sketch them in one system of axes and see what comes out. My example says, represent the following set of inequalities on the same system of axes. You're given 2x plus 3y less than 24, x plus y less than 9, x less than 20, y is between 1 and 7. I have actually already drawn that on the right-hand side here. But I would like to pose a challenge right away. If you take a second to look at that graph, looking at the inequalities, what is wrong with that? Okay, I will redraw this. Maybe you can pick the answer as I do the question. So you're given here that X and Y are basically some production items, like you've indicated. You could be having trucks and kumbis and all those kind of things. So let's proceed and draw this. All right, let me extend my page there. So A straight line. A straight line is one of the functions that's so easy to sketch, guys. Remember, we need to know the defining features. Defining features of a straight line, it must maintain the slope, same gradient throughout, and it's got one x-intercept, one y-intercept. Of course, it could have zero y-intercept or zero y-intercept, depending on whether it's a vertical line or a horizontal line. In this case, if we want to, if we look at the first equation, inequality, it says 2x plus 3y less than 24. Now, if you can deliberately cover that part of the equation, just because y is equal to 0 if you are looking for the x-intercept, you end up with 2x equal to 24. That results in x, in this case, x less than, because this is now an inequality, x less than 12. All right? Now, that was the x-intercept. The y-intercept of that, I will have to cover the x part now. The x term, if I can quickly rewrite that. Now you're going to cover the x part because x is equal to 0. Now you're left with 3y equal to 24. If you divide that by 3 throughout, you're going to get that y must be less than 8. You're now in a position to represent this on a system of axes. In this case, let me already prepare it. All right? We are going to mark x equal to 12 and x equal to 8. All right? Then we join these two. Okay, so of course we could proceed, but there's no production below x equal to 0. So I will represent this with x, and that will be my y variable. Now, what is wrong with this? I don't know if already there are answers streaming in for the question I asked.
Well, so far, I'm checking. I'll let you know if I see anything pop up.
All right, let me proceed. I'm going to deliberately draw it wrong anyway, just until you give me the answer. All right, I'm going to draw it like that. And I move to the second. Okay, there we are. All right, let's extend this page. I think the second one said x plus y less than 9. So x plus y less than 9. The procedure is the same. We are going to cover the x part and get the y-intercept. Cover the y part and get the x-intercept. So you are going to therefore get x less than 9, and the other part is going to be y less than 9. So I'm going to mark those two. Remember, this was 12. Was it y equal to 8? And that was 12. Okay, we now have x and y at 9 and 9. You have to plan your axes very well if you're not given a graph paper. So this will be 9 over there and 9 somewhere there. You join those two. Okay. The third constraint says x must be less than 20. Yes, you can produce all these x items, but they must never be more than 20. My graph is a bit, all right, short of space there, but I will represent 20 at that point. So if this was x equal to 20, all right, so that is, yes, of course, I need to represent these things as inequalities. In fact, let me retrace this quickly. So for this line, I needed something that is less than the y values that are less than that graph. The other graph, quickly, that would have been graphs that are less than that. I mean, values that are less than that. for this particular one, it said x less than 20. Of course, we show it in that direction. Okay? A bit of a mess there. All right. Then comes the third constraint quickly. It says y must be between 1 and 7. 1 and 7 units. This is a bit straightforward in the sense that all you have to remember is that you are dealing with y only. So if y is 7 there and y is 1 there, so you are saying below that and above 1. Okay. And one of the constraints that we call implicit constraints is the fact that you can never have negative production. So your x must be greater than 0. They didn't tell you, but it's more like obvious. Okay. So if we look at those inequalities, below this, you've got that area, and below that, you've got that. If I can show these arrows inside there, and up like that. So when you have shaded that region, it's one of the areas that's very important it's going to help you with decision making. It's called the feasible region. All your solutions will come from that region. All right? Solutions typically come from the vertices of this polygon. You can call it a polygon. Okay. Mark that. These are your vertices of the polygon, and that is called the feasible region. So if I can mark it there, feasible region. So all the solutions should come from inside there or at the vertices of that. Now, earlier on I asked you, I gave you a challenge question, and I said, what is wrong with it? What did I miss out? And do you have anything? Because I'm going to give the answer now.
Not yet. I think it's good to go.
All right. So what is missing with this thing is the fact that this line, I've made it solid. All these lines, I've made them solid. Yet the inequalities do not say less than or equal to, or greater than or equal to. So that's one thing we need to retrace and say, let me take a green pen just to highlight what I'm talking about. So we basically have that. If I can just show it as dotted lines, because the values at the boundaries and at the vertices are not included in this case. That is what the challenge question was about. And I'm going to stop here. Heather will come and do the second part, and I'll come back again.
All right, no problem. So guys, while we do our Houdini, and we'll be back just now. And guys, make sure you get in those posts, because I still have a calculator and a labeler to give away, but we'll see you just now. Welcome back, Mindsetters. I hope you had a nice little break. You grabbed whatever you needed in terms of your snacks and everything, so you don't have to get up again or move around, so you can pay attention. But right now, I'm going to hand you over to the ever-lovely, ever-glowing Heather, who's going to take you for the rest of this session. So, Heather, take it away.
Thank you, Ty. Hi, guys. Very warm welcome from me. So basically, just to recap what E.T. did in the previous section, what he did was he gave you the most basic kind of question you can get in linear programming. They gave you all of the constraints in their algebraic form, and all they wanted you to do was to draw those constraints and then to shade a feasible region. Okay? Now that's the most basic thing, but that's why we started with that question, is because you need to get your basics in place. All right, what I'm going to do with you now is I'm going to do the second kind of question that they can ask you. And basically, that is going to be, they give you the drawn feasible region, and you have to take it backwards and give them the constraints. That's the second type of question. The third type of question, which E.T. is going to do after I'm done, is one of those ones where it's the wordy type, where they give you that there are 4 buses and 9 trailers and whatever, or there are X number of students and Y number of teachers going on a trip. Okay, so can you see how we try to lead you through this section so that it's not quite so daunting? Okay, I've said enough. I tend to sometimes overtalk, don't I? Okay, so literally what I'm going to do is I'm going to look at this feasible region which has been shown, and our first task is going to be to write down all of the constraints. Okay, now guys, what I want you to first of all have a look at is that, as E.T. said, let me make sure that you understand that when I use my actual computer program, all right, this is the bit here that you normally see as blank, and this is the bit in here that is normally shaded, okay? So my computer program just makes it a little bit more different. So that is the area that we're going to be looking at, okay? So this purple area is my feasible region. So the first thing that I make my candidates do is I make them actually label all of the corners. So my feasible region actually goes A to B to C to D to E and to F. All right? So literally I have got a feasible region called A, B, C, D, E, F. All right? It's not your normal kind of triangle. It's a little bit more of an interesting shape than that. Now, I want to get down all of my constraints. Okay, so let's start at the very beginning. Can you see that by writing down my feasible region, I can actually see that I've got to describe what is happening from A to B. This line or this barrier here, A to B. Now, because my picture is drawn to scale, I can actually see that my X value here is what is being described. And can you see that this is an X value of 15? So literally my first constraint is going to be about a vertical line, and X is to the right of, so it's greater than or equal to 15. Okay? So that is my constraint literally running along from A to B. Right, now I'm going to go from B across to C. And now that is a horizontal line, okay? Now if I read back to the horizontal, all right, can you see that it reaches here at 20, and that means that my Y value, all right, for this shaded feasible region has to be less than or equal to 20. Okay, we're going good so far. Then I have to go from C to D. Right, now C to D, you can see is a skew line. So I'm going to need to work a little bit harder from C to D. Now let's just go down here and have a look at what we're going to have to do. Now, guys, I'm going to show you two ways, and you're going to have to decide which way you prefer. I know that CD is of the form y equals mx plus c. It is a straight line, okay? Now, if I have a look at this line CD, it cuts here at 30, and it cuts here at 60, all right? Now, that immediately tells me that my y cut, all right, is going to be 30. So I've got that reading it straight off of my axis. So my y cut is 30. Now what I need to do is work out my gradient. Now visually, I don't even need my formula. I can see that if I was going to get from this point to that point, as x increases, can you see that what I would be doing is going down 30 and across 60? So my gradient would be down 30 units and across 60 units. Okay, down 30 till I got to the origin, across 60. So my gradient of this line is actually negative a half. Okay, so what I now have is my constraint for CD to be y equals negative a half x plus 30. Now I just need to have to check the relationship. Can you see that my feasible region is actually underneath that constraint? And when it's under, it means that the y values are lower than the line, so I need to actually change this and make my constraint into negative a half x, add 30. So that is my constraint for CD. Right, but now I don't like to make promises and not carry them out. So what I'm going to do is show you an alternative way of working out CD. All right, now I want you to notice that you have the y cut and you have the x cut. All right, the y cut is at 30, the x cut is at 60. Now when you have that information in a line, then you can find the equation of that line by using this natty formula. Okay, now, some of you may have seen this before. I hope you have. If you haven't seen it before, it's only going to be used if you've got the x cut and the y cut. Okay? So, remember I said that my x cut was at 60 and my y cut was at 30. And this is how fantastic this formula is. So you put x and you divide it by the cut, which is 60, and you put y and you divide it by the cut, which is 30. All right, let's just try and get rid of what's happening here. We divide it by 30, all right, and we put that equal to 1. Now, that's fine. That in that form is fine, but it's not much use to us to be able to see the inequality. So if I got a common denominator of 60 throughout, this would be x plus 2y is equal to 60. All right? Now, can you see that if I actually got that into the y form, it would be 2y is equal to negative x and 60. And finally, dividing by 2, it would be y is equal to negative a half x and 30. All right? And so I'm going to be drawing a big fat smiley face here because hopefully you can see that that is exactly the same answer as I got there. Y less than or equal to negative a half x plus 30. So all I would need to do is just make that a less than or equal to, and I've got exactly the same constraint. In fact, even if I had not got it into the y form and I had just done that, then that would be fine as my constraint for CD. So just to reiterate, when I say that would be fine, I'm going to put a smiley face there and I would get all my marks. The only reason I took it to this was so that I could compare. Right, we're on such a good roll because now we've done CD. We now just have to keep on going and fill in our CD. So our CD was y less than or equal to negative a half x and 30. So that's that constraint. Now we've got to do DE, and you can see again that DE has got something to do with x, and so DE is definitely going to be x less than or equal to 40. Now at this point, mindsetters, I hope that you're saying, can't we combine those two? Well, of course we can combine them, okay? And normally in maths, we would combine them as 15 less than or equal to x, and I think maybe you might not be able to see that, so let's just quickly get rid of that, hopefully, and let's see if we can see 15 less or equal to x less or equal to 40, and hopefully you can see that. So both of those x constraints, can you see you've got a minimum x value and a maximum x value, and the x is kind of wedged in between them. Right, so we've done DE. Now we need EF. and I'm going to put in EF over here. And can you see that EF, again, is going to be in terms of y. It's a horizontal line, and if we read back our scale, it's y greater or equal to, because it's above, all right, 5. All right, and again, you write. Can you see that this chappy here and this chappy here can be put together as one constraint, all right? And that constraint we could write as 5 less or equal to y less or equal to 20. All right? If you don't put them together, it's not the end of the world, but it's just more kind of succinct. It's more kind of accurate, more mathematically pretty. Okay, right, we're nearly there because the only constraint that we've got to talk about now is AF. And I'm not going to do it both ways. I don't want to waste too much time with that. But what I can see from the start is that it goes through 30 and it goes through 30. And so that's exactly what I'm going to try. Is going to be for that last bit. I'm going to use an X going through 30, a Y going through 30. And so I would get X over 30 and Y over 30. And it's always equal to 1, guys. That never changes, this new fancy way if you've got your X cut and your Y cut. So again, I'm going to get X plus Y is equal to common denominator, so that would become 30. And so the area, first of all, I would have to take it as negative X plus 30 by taking that over. And let's go back and check. Which area am I wanting? Can you see I'm wanting this area here? How would I describe that area? Well, in comparison to my line, it's above, and above means more, whereas below would be under. So when I do my constraint, I would definitely be wanting y greater or equal to negative x plus 30. Right, so guys, that kind of question, all right, really is not meant to be difficult. But you can see that it tests everything you know about straight lines. Okay, I'm going to move on to the next concept that talks about actually once you've got your feasible region, which remember it's this bit here, the whole thing about linear programming is normally to minimize or maximize, okay? And the question says is that we want to minimize P equals 2x plus 5y according to the feasible region, okay? Now, normally in these questions, P stands for profit, okay? So normally you're making 2 rand off of every X item and 5 rand off of every Y item. And we want to minimize this. Of course, we can maximize it as well. So what is our method? All right, we take our P is equal to 2x plus 5y, and we get it into the y form. So that means I'm going to actually take the 5y, okay, is going to be equal to negative 2x and p. So please notice I've kept my y positive, and I've just transposed this onto the other side. However, getting that into the y form tells me that I'm going to get negative 2 over 5x and p over 5. Okay, now guys, this is called maximizing using a search line method. What we do is we focus on that thing there. Now notice that what you have here is a whole family of lines with a gradient of minus 2/5. Okay? Now if we go to our feasible region and we put in a line with a gradient of minus 2/5, and I'm going to actually use this big red line, all right? It's going to start it there, and it's going to go all the way across to there. Okay, now that is a line that has the gradient of minus 2/5. But I could have actually put in another line with a gradient of minus 2/5. And I could have said, okay, that's the same as a line with a gradient of minus 1 over 2.5. Can you see it's the same ratio? I divided the top by 2 to get 1, and I divided the bottom by 2 to get 2.5. So if I had rather put that line going from 10 to 25 over there, all right, can you see that both of those red lines have got gradients of minus 2 over 5, okay? But this one hits the axis, the y cut, all right? This one hits the y cut, this thing, as low as 10. This one thing hits the y cut as high as 20. And we are wanting it to be minimized. So in fact, this red line has got a lower y cut than this red line. And we want it to be minimized, okay? So basically, guys, what we have to do, and I'm going to just see if this is going to work for me, what we're going to have to do is we are going to have to take this line, all right, and move it. Oh, and it doesn't want to move for me, all right? It's not going to, yes, it is, there it goes. And we want to move it. And if we move it, can you see that the first place that it hits in my feasible region is right at that point, okay? If I wanted to maximize, I would have to take it, and then I would have to take it to the last place, and it doesn't want to take it. It's being naughty. Okay, but basically, when I want to minimize, I want to move this line until such time, all right, as I actually hit it for the very first time. And it hits my feasible region there first. Now, what is that point? Well, I can read off that that is the point, and I hope that you can read what I'm writing here. That is the point 25 for x and 5 for y. And so if we go back to our question, it says minimize that according to the feasible region. So I know that because my search line hits that point first, those values are going to actually be the minimizing solution. So all I have to do now, guys, is I just have to substitute in. So I'm going to get P is equal to 2 times 25 plus 5 times 5. And that means that I'm going to get 50 and 25. And so the minimum value that P can ever be is 75. All right, so before I go for a break, what I want you to remember is that once you've got your feasible region, in order to minimize or maximize a given expression, you have to draw in a search line, and then you have to move it. Oh, there it goes. Look how magic that was. It moved it, okay? And you have to move it until such time as it hits your feasible region first. That will minimize. And if we keep on going until it actually minimizes or hits the feasible region last, then that would maximize. Okay, so I hope that you've been following. Ty, have they been following?
Yes, they have. Everyone seems to be loving it. Like Kamuhelo's like, this is my favorite subject.
Oh,
She's like,
awesome.
Awesome.
Okay. I must say that this particular topic, if they can do the question, it just flows because it's not difficult really.
Once you get it, you get it.
It's the same process over and over again. Okay, good. We're going to go for a break.
All right.
Cool.
I think so.
Good.
So guys, make sure you keep posting. And if you're enjoying it like Ashworth and Kamuhelo, keep posting. Because guys, that's what it's for. It's for you guys. And remember, I still have to give away this calculator and a labeler. So guys, make sure you stick around. We'll see you after this break. Welcome back, Mindsetters. We had a nice little break, as I always say, and I hope you have your pens and pads out and you guys are ready to make notes. And while we've done our little magic trick and we swapped around people. Guys, don't worry, we're still doing the same subject content. So make sure you're paying attention, because this next session is also pretty important. So guys, pay attention. And to those who are writing pretty soon, good luck. But yes, you especially need to pay attention. But for now, I'm going to hand it back to Mr. E.T. Mr. E.T., take it away.
Thank you, Tai. Yes, I've got two questions that I was going to ask today, but I think I'll start with this one. I'm not sure if I'll be able to do the last one. What I always tell my learners is that information basically will be converted from one form to the other. So I can ask you, having given you a graph, I can simply ask you to to work out the equations. And I can give you the equation, and then 1 to 2, convert it to a graph. Or I could just give you a problem statement from which you have to determine the other two types of information. The problem that we have today is basically covering all of that. It's taking us through two steps. It says here's the problem statement. You have the owner of a pleasure boat who's prepared to take a school group consisting of learners and adults on a cruise, provided that the group consists of no more than 60 people, and in addition, there must be at least 35 people in the group, there must be at least 6 adults in the group, there must be not more than 14 adults in the group. So you'll notice that there is a certain language that we are beginning to talk here. We're talking things like not more than, pick a pen there, no more than, and we're talking about the language of at least, there it comes again, not more than. You could therefore have the opposite of that. You could have the not less than, the at most, that kind of language, not exceeding, or you have a maximum of this. So you need to get used to that kind of language when you read this kind of problem statements. And here we're given, let me just read further. Let X represent the number of learners and Y the number of adults, and answer the following questions. So you're going to give us the constraints in terms of X and Y. Let's begin with the constraints. This is more of a leading question because it takes us through steps, to building up into what we want to do. All right, so we did say that this group of people is made up of learners. All right, let's see, learners and adults. Now, they are suggesting for us that we let learners be represented by X and adults be represented by Y. So, as we read the question, it was talking about X plus Y, basically the total not being more than 60. So already you can write here X plus Y must not be more than, which means it must be less than, must not be more than 60. Yet, the additional information that we've been given says here there must be at least 35 people in the group. So that suggests that we need, for this guy to be able to do business, he's going to require that at any given time, he's got more than 35 people. Otherwise, he's not going to do a trip. All right. What else do we have? We are supposed to give all the constraints here. That is the first constraint. And the second constraint is that, if you read section number B there, it says there must be at least 6 adults in the group. And adults are represented by Y. So if we say at least 6, it means we must have more than that. So for that, let me just create space here. Quickly. All right. So for adults, we are going to have Y must be greater than, what did we say? We said there must be at least 6 adults in the group. So that must be greater than 6. I've got the first constraint, that's the second constraint. Any more information to that effect? What I've underlined basically is leading me into the constraints. The next set of information says there must be no more than 14 adults in the group. Again, it's pertaining to the adults, both statements. So it says not more than, so which means we also have that y must be less than or equal to 14. Like Heather showed earlier on, you can combine these two inequalities into one, where you're saying you must have your numbers between 6 and 14. So the number of adults must be between 6 and 14. All right, let's see if we have covered everything. Those are two constraints that we have created there. And another one, I did talk about the implicit constraints. Definitely, the y has already been specified as between 6 and 12. Now the x definitely must be greater or equal to 0. It's just one more implicit constraint. All right, and I think we have covered all the constraints. If I look at that, then let's go to the next question. It says if the group has 25 learners, what is the minimum number of adults that must accompany them? Right? So this is now a group, which means the total. Right? We said a group must be more than 35. So essentially we are saying x plus y is supposed to be greater than 35 on the minimum side, because now the 60 is on the maximum side. Then if you say to me there are 25 learners, x represents the learners, I'll simply put in where I see x, I'll simply put 25, and what comes up is 25 plus y must be greater than 35. So this means therefore that my y, the others that can accompany the learners, must definitely be more than 10 adults. You need more than 10 adults. That's a minimum for this guy to be able to do the business. All right, if we go back to that and carry on, we've answered the second question. What is the minimum number of adults that must accompany the learners? The third question says, 8 adults offer to go on a cruise. What is the maximum number of learners that can be accommodated on the boat? Now, on the maximum side of the group, we said it is less than or equal to 60. And here we are talking about how many? 8 adults offer to go, yes. So on the maximum side, we've got x plus y is supposed to be less than or equal to 60. But now if you have y equal to 8, which means the number of adults is 8. So we're going to say x plus 8 must now be less than 60. So from there you can see that x is going to be the number of learners that can come in. X is going to be 52. 60 minus 8 is 52 learners. And that, hopefully we have answered the question correctly. Yes, they were asking for maximum number of learners. So you can accommodate easily 52 learners. The fourth question says, if T is the amount in rent paid by the whole group, what is the cost per learner if your T expression, which means the revenue of the guy who's doing the business? So this is the expression that they gave you, okay? Now they want to know what is the cost per learner. Now the number of learners is represented by X. Just by looking at the equation, you can see that you have multiplied cost per, let's say it's dollars per number of learners or number of people, and you multiply by the number of people. In this case, the number of people is X. So our answer to that is pretty straightforward. It's equal to that coefficient. The coefficient is 30. that is the amount in rand. In this case, it's in rand. That's the answer to that question. Pretty straightforward. Question number 5 says, represent the constraints graphically and clearly shade the feasible region. You can see that we are going through all the steps of converting information from one form to the other. We started with a problem statement. We converted these things to equations, inequalities. Now we're going to express it graphically. So this is what the 5th question is asking for now. Right? The feasible region and all that. We're representing all those inequalities in a graph now. I would like to list them quickly here. All right, we did say x plus y less than or equal to 60 and greater than or equal to 35. And if I can just list them in one line, the other one was, if I go back quickly, was y between 6 and 14. Okay. Y between 6 and 14. And lastly, we said, without doubt, you need to have a number of learners, either 0 or at least greater than 0. All right, now we want to take this and represent it graphically like I did earlier on. Okay. So if we draw, okay, maybe rearrange this because there will be 2 equations that come out of this. All right? So what will come out here is one equation will be x plus y greater than or equal to 35. The other equation will be x plus y less than or equal to 60. All right? Yeah, over there, same story. Y greater or equal to 6, y less than or equal to 14. So I've got the whole list here. So we are in a position to, we've got x greater than 0. So we're in a position now to represent these things on a graph. There we go. Like I said earlier on, all you do is cover your x part, considering that x equal to 0, to find the y-intercept. Now you know y is going to be 35. This is going to be your y-axis, and that's your x-axis. All right, so if we work on the maximum here, let's just plan our axis here. Okay, if we start with this, we see that we're going to need a 60. All right, so let's mark it so that we have 60 there, and somewhere there it's about 30, and we don't get surprises here. 30 and 60 there. All right, I'm just looking at the minimum and the maximum. Everything else fits into those two big numbers. So over here, if I cover the x part, and I end up with y equal to 35. So I mark that point there. Same story, if I cover the y term in the equation, I end up with x that is 35. Somewhere up there. And I join the 2. All right. And notice that I'm now making it a solid line because I did say greater than and equal to, or less than or equal to. All right. And if I move on to the other one, I do the same approach. I cover the x, I get a 60. I cover the y, I get the x-intercept. So I join the 2. That's my inequality. But, of course, I need to represent that with the arrows. The inequality is greater than. And this one says less than. All right. I'm left with 3 more inequalities. The one says your x must be positive. Surely, I don't have a problem with that. I'll show it over there. Anything that's to the right of the y-axis. For the y, you've got y equal to greater or equal to 6, and then 14. So that comes to somewhere there, 14 and 6, somewhere there. And I said greater than, and I said less than for 14, and for 6, I was at that point. So there comes that thing. Okay, let me shade my feasible region. It's simply that part. All right. But what you will see, therefore, is that some of these inequalities or constraints are basically redundant. I didn't have to mention that because, automatically one of the vertices. All right, let's just get that. All right, that's fine. So I could have done that, yes. All right, so that basically, we did have this thing going this way. So saying x greater than 0 was not even important, but that's the essence of those redundant constraints I was talking about. But there is our feasible region. All right, I think we have basically just answered the fifth part of the question. I think the last one was, all right, I don't think I'll be able to, what is the composition of the group if the owner's income is as large as possible? There comes that part where Heather was basically taking the equation of, the function, and then translating it across the feasible region to determine the maximum point. Right? I don't know if there is anything streaming in, otherwise I don't have more time to carry on with this.
No, besides that, they're enjoying the lesson and people are following along. A little bit of confusion here and there, but that's the thing. I always tell them, if you guys are confused anywhere, please make sure you specify. But otherwise, I think we're
Not
good.
specific. Yeah, thank you.
All right.
Okay.
So guys,
All right.
guys, I'm going to do my best to hunt down the rest of you people on the page to get you guys the stuff. I don't know, Mr. E.T., do you want to say anything else? Do you want to add on?
Not really. I don't know. I think I will carry on next week.
All right.
Yeah.
So on that
definitely.
note,
Yeah.
guys, make sure you keep posting on the page, keep chatting to us, get all your questions. If you're lost anywhere, if you need help, make sure you post to us, because we can't help you if you don't help yourself and post on the page, because then no one gets help. But guys, as I said, I'm going to hunt down the winners of the stuff, so I'm going to make sure that you guys get it. And guys, I just want to send a quick shout out to Liberty. Thank you for sponsoring. And from me to you, I'm going to say take care, and we'll see you next time. Cheers.